2 notes all about reaction energy. And so we are going to start in class by exploring a little inquiry mini lab and looking at this, but for the sake of the notes, we're going to dive right in. Like I mentioned in concept 1, some physical changes, like state change, involve a transfer of energy, but all chemical changes and thus chemical reactions involve a transfer of energy. And so that's what this concept is about, that reaction energy and that transfer of energy that we see in chemical reactions. Now, collision theory this should be a refresher from Unit 5, chemical reactions, where this was first introduced. But this is the concept that reacting particles must collide in order for a chemical reaction to occur. And they can't just collide. They can't just, bump into each other. They have to do so with enough force to actually change something. Okay? So they can collide without actually reacting if there isn't enough energy involved. So there has to be enough energy in their collision for something to change. And the rate of a chemical reaction depends on the frequency of these collisions between particles, which we'll talk more about in concept 3, which is our reaction kinetics. But for now, we're just going to focus on this energy. This is like one of the most important, these next 2 slides, distinctions that I can make for you in your science career, especially those of you who are biologists and are into biochemistry. Like, you have to understand this. Bond breaking requires energy to be absorbed. Okay, because every bond has a certain amount of bond energy, and it's the amount of energy needed to break that specific bond. Okay, so for example, 2 carbon atoms single bonded together has a bond energy of 347 kilojoules per mole. That's how much energy would need to be absorbed to break this single bond. Now, that number means nothing to you, so let me give you some context. A double bond between 2 carbon atoms has a bond energy of 614 kilojoules per mole, so it takes a lot more energy to break this bond. A triple bond between 3 carbon atoms would have 811 kilojoules per mole of bond energy, okay? So this is what I'm saying. Energy has to be absorbed to break these bonds. And the activation energy is what we say is the minimum amount of energy needed to get particles to collide with enough force to start a chemical reaction. Okay, this is the energy we need. Looking at this diagram, we haven't really gone through potential energy diagrams yet. We are in just a minute. But looking at this, notice it's showing reaction progress. So as we're moving to the right, the reaction is happening. And energy, okay? So A represents our energy at the start of the reaction. What energy is in the bonds of the existing reactants in this reaction here, okay? From here, from A to C, that's our activation energy. That's how much energy needs to be input in order to break up the bonds that are existing between these hydrogen atoms and between these iodine atoms. Okay, this has to be input to break those bonds. And then once those are input, we see that energy starts to be released as bonds are formed, because bond making results in energy being released. So as new bonds are formed, energy is getting released, and that's why we start to see this line go down. So the line goes up as energy is added in order to break bonds, and it declines as energy is released as new bonds are formed when we make this hydrogen monoiodide. Okay? So looking at the difference though between A and B, what we start with and what we end with, that's where we can identify a reaction as being endothermic or exothermic. Okay, so hear me very clearly. All reactions involve both an absorption and a release of energy. And so when we're classifying a reaction as endothermic or exothermic, that's based on changes in the overall bond energy, the total bond energy, the net energy, if you will, okay? So an endothermic reaction is a reaction with a net absorption of energy, because yes, energy is being absorbed and energy is being released in the reaction, but overall more energy is absorbed than is released. And we see that we get a positive delta H in an endothermic reaction, which I'll explain what this means in just a minute. Exothermic reactions, on the other hand, have a net release of energy. Okay, so energy is absorbed to break bonds. It is released as bonds are formed. And overall, we see more energy is released than absorbed. Thus, we would classify it as exothermic. Okay, and now let's bring back in that potential energy diagram, because I really feel like looking at these diagrams helps so much with understanding the energy exchanges in a reaction. So a potential energy diagram, it's just a diagram of the changes in potential energy. Remember, the chemical potential energy between bonds, that's what we're talking about here, of these atoms. And it's looking at how that changes throughout the course of a chemical reaction. Okay, so let's look at this example again. This is looking at this reaction of, hydrogen and iodine making hydrogen monoiodide. Okay, so let's label each of the parts on this. I would label these in your notes so you can understand what this is showing you. Okay, so A is showing me, I color coded it in blue here and here. That's showing me the energy stored in the bonds of the reactants. That's the level of energy that they have within them, because that's where reaction progress is at the beginning. That's what we're starting with. Okay, B, I color coded it orange, shows me energy stored in the bonds of the products. So notice the reaction progress on here. This is where we're ending, okay? Now, C to A, the difference between C to A, this hump here shows me the activation energy needed. It shows me how much energy needs to be absorbed to break the bonds here in order to eventually form new bonds. So this has to be the input of energy to get that collision theory happening, to get those reactants to collide with enough energy and force to actually change. Now, this difference here from B to A shows me the overall difference in energy of the reactants and products. Because remember, energy gets absorbed in order to break bonds, and then as new bonds are formed, energy is getting released and thus it goes down. Now, to look at the overall change in energy, we just have to look from the start to the end. That's what we see with B to A here. When we look at this difference, that's our delta H. That's going to tell us if this reaction is endo or exothermic. So you're going to take the final minus the initial energy and see what you get. If it's negative, okay, that means the reaction is exothermic. You ended with less energy than you started with. It's negative, thus overall energy got released. More energy was released than was absorbed. If it's positive, that means that there would be more energy in the products than there was in the reactants. So energy must have overall been absorbed. It's an endothermic reaction, okay? Let's look at these a little bit side by side. I think that will help. So looking at these two potential energy diagrams, look at the difference. First, notice they both have an activation energy. They both require an input of energy to get the reaction started. And after that input of energy happens, we notice the line starts to decrease on both. As new bonds are formed, energy is getting released. This is going down. Now, look at the difference in the ending and the starting. Notice in this first picture, we have more energy in the products than the reactants. In this one, we see we have less energy in the products than the reactants. So in this first one, energy overall is getting absorbed. And so we would say this is an endothermic reaction. Whereas over here, overall energy gets released, so it's an exothermic reaction. Now, something that can change the look of these potential energy diagrams is something called a catalyst. The addition of a catalyst to a reaction will impact this energy exchange. So a catalyst is a substance that speeds up the rate of the reaction without actually being changed by the reaction, okay? It's not a reactant, it's not a product, but it can change the reaction by lowering the activation energy. So watch that again. Look at this picture. Boom. A catalyst would be this additional line here. I put it in yellow to match the word catalyst. Notice that we start and end with the same amount, but we need less energy to get the reaction going. That's what a catalyst does. It lowers the amount of energy needed to get those initial bonds to break. And we can see it on this diagram too, what that looks like. So it lowers the activation energy needed. Okay, we're going to practice working with these energy diagrams in just a little bit towards the end of these notes, but I want to introduce you to two other terms before we wrap this up: entropy and enthalpy. So the transfer of energy during a chemical reaction in a closed system, it involves changes in the energy dispersal, which is known as the entropy change, and also the heat content, which is the enthalpy change. Okay, I remember the difference because heat has a T and an H, and we see that in enthalpy. We see the heat here. And then entropy has the R like energy has an R. I don't know if that helps, but it helps me. Okay, so We see changes in the energy dispersal and heat content while assuming that the overall energy in the system is conserved. Why? Because of that first law of thermodynamics, the law of conservation of energy, that says no energy should be lost during an energy transfer in a chemical reaction. So even though we see these changes in how energy is dispersed and the heat content, we shouldn't see an overall loss of energy, okay? Now, a second law of thermodynamics I want to introduce you to says that energy tends to disperse or spread out. Okay, it doesn't tend to stay clumped up. It tends to spread out. Okay, so this is why heat always spontaneously flows from higher temperature objects to lower temperature objects. Okay, why does it do that? It does that because it's spreading out. Okay, so we tend to see in spontaneous reactions an increase in entropy as we see an increase in how things spread out, and we see a decrease in enthalpy as the heat kind of moves from higher to lower and goes that way. Okay, but we'll talk more about that in a second. So more on each of these terms. Entropy is represented by a capital S. It's a measure of the degree of randomness of particles in a system. System, I've said that a couple times. When we're talking about a system, we're just talking about the chemical reaction and what's going on there. And then the surroundings are just like everything else. Okay, so I like this picture because low entropy, you see the order. High entropy, you see the randomness and more of the disorder here. And entropy impacts whether a reaction will occur spontaneously. Like I said previously, nature tends to move towards increased randomness, so towards more disorder and towards a higher entropy due to the second law of thermodynamics. Now, enthalpy is represented by a capital H. It refers to energy as heat content in a system, but it isn't really practical to talk just about enthalpy because we can't directly measure that. So what we do measure is that delta H, that enthalpy change. We look at the amount of energy absorbed by a system as heat during a process at constant pressure. So if that's positive, that means energy did get absorbed and it's an endothermic reaction. It's greater than zero. If you were writing a thermochemical equation, like I mentioned, you'd have your reactants plus your energy yielding your product. If it is negative, that means it wasn't absorbed, okay? It means it was released, and that's your exothermic. And so that's where we would write the thermochemical equation as the reactant yields the product plus your energy. So delta H is just, your H of your products minus your H of reaction. So we're looking at energy stored in products minus energy stored in reactants. Again, if it's negative, we say the reaction is exothermic. If it's positive, we say that the reaction is endothermic. Okay, now we're going to kind of look at this and practice a little bit with energy diagrams. And that's your concept 2 notes all about reaction energy.